Hi budding engineers, welcome to Structural Engineering Lectures and welcome to the new playlist on the analysis and design of structures using STAAD.Pro, ETABS, Excel sheets and spreadsheets and seismic and wind analysis. In the previous class we have seen analysis and design of RCC building substitute frame using STAAD.Pro, and we have verified with manual calculations, right? In confirmation with IS 456 and SP 16 1980, which is the limit state of design of RCC code, right? For plain and reinforced concrete, right? In today's class we shall see the analysis and design of a single story RCC building by STAAD.Pro, and it's a tutorial. We'll design the slab, beam, column, footing by manual design as well as Excel spreadsheets, conforming to IS 456 2000, which is a limit state method for concrete designs. Right now, before we see the actual discussion, student, let us see the brief profile of the speaker, right? That is mine, right? I, Dr. D. Rupesh Kumar, obtained my BTech in civil engineering from Nagarjuna University in 1994 and MTech structural engineering from JNTU Hyderabad in 2000 and PhD in structural engineering from JNTU Hyderabad 2009. Presently I am working as associate professor in Department of Civil Engineering, University College of Engineering, Hyderabad, Telangana State. Right? I have an experience of 27 years, of which 7 years is in industry and 20 years is in teaching and research at graduate and postgraduate levels. Right? My research areas include the reinforced cement concrete designs, steel designs, structural analysis, point element analysis, earthquake engineering, bridge engineering, structural optimization. I have published 45 research papers in international, national journals, conferences, and organized 3 international conferences and 11 international conferences, workshops, attended 43 workshops, visited 2 countries, and delivered 13 guest lectures and edited 3 books, supervising 14 PhD scholars and supervised 30 ME theses. I am presently actively involved in various consultancy works that are offered by the department and completed over 750 design proof checks and 150 designs of RCC, steel, composite, low-rise, high-rise, multi-storied buildings and road and rail bridges. Right? Once we see the brief profile, student, now let us see what will do the analysis and design of a multi-storied building. Now I'm just showing the frame consisting of the beams and columns of a this ground floor or single story 3-room building. Right? Now let us examine the data, student. This is the data given. Right? Now analyze and design, right? Analyze and design or analysis and design of RCC 3-room ground floor building conforming to IS 456. Right? What is now given? The data is analyze and design the slab, beams, columns and footings at ground of a ground floor building. Now this is how the ground floor building is shown, student. Right? This is how what we are trying to do, right? Wherein this ground floor building is having no plinth beams, and the walls are directly supported on the CRS masonry. Right? That is how the data given. And the other data what is given is take the thickness of the brickwork as 230 mm and size of the doors, just now we have seen, right, 0.91 meter by 2.05 meter, and the size of the windows as 0.91 meter by 1.22 meters, and assume no plinth beam at the plinth level. Right? Therefore there is no plinth beam at this plinth level, student. Right? That is what the data also given. Right? And use M20 grade concrete and FE 500 grade steel. Assume the safe bearing capacity of the soil as 200 kilonewton per meter square. Now assume the plan consisting of 3 rooms, each of 4.54 meter by 3.54 internal dimension. Right? That is how I have to have 1 plus 1 plus 1, 3 rooms, right, which is 4.34 by 4.54 by 3.54, right, each of 4.54 by 3.54, right? That is how the internal dimensions are given. Now I need to design the slab, beams and columns and footings. These 4 components we'll see manually as well as using the STAAD as well as Excel sheets. Right now. That is how the data given should. Now we can see this is the cross section of this frame, right, which is 3.2 meter height, right. The columns are 3.2 meter height, right. That is how here I do have the columns 3.2 meter height, right. Obviously this 0.2 meter is there in CRS masonry level, right, remaining just above that floor finishing level 3 meters. That is what my assumption, right. Below that it is presumed that I do have sufficient safe bearing capacity of 200 kN per meter square. Therefore the columns are embedded in the footing, which is having an SBC of 200 kN per meter square, right. That is how the data given, student, right. Once we see this the given data, now let us move quickly to that of this plan, right. These are the plan 3.54 by 4.54 meter each internal dimension, rooms and height also just now we have seen, and we'll be following this xy, right. And this just now we have seen the thickness of the brickwork given is a given data, student. Thickness of the brickwork given as 230 mm thick, and M20 grade concrete means FCK, characteristic compressive strength of the concrete, is equal to M20 means 20 Newton per mm square, and Fe 500 means the yield stress of the steel is 500 Newton per mm square, and SBC of the soil is given as 200 kN per meter square, and the clear span between these brickwork to brickwork, right, is 4.54 in the length direction as well as in the width direction. It is 3.54, right. Now what now I'll do is I'll initiate first of all the designs of the slab, student, right. I'll initiate the designs of the slab, then I'll go to the designs of the beams, then designs of the columns, and finally designs of the footings, right. Now first to start with, I'll propose the designs of the slabs using manual calculation to start with. Therefore now I'm assuming the depth of the slab from the past experience as say 125 mm 5 inch, therefore capital D is equal to 125. Hence the effective depth of the slab, assuming 15 mm clear cover, and I'm assuming that 8 mm diameter bars I'm using, right. Therefore I do have effective D, small depth, small d is equal to capital D minus 15 minus 8 by 2. It works out 106 mm, right. Now obviously once I get this effective depth, then I can calculate the effective span of this slab as per this IS 456 2000 class 22.2 B, page number 35. Let me just quickly move to that page number 35, student, right. This is this page number 35, right, wherein I do have this effective span for simply supported or beam or slab. Now I do have continuous beam or slab, right. Now code says that in the case of the continuous slab or beam, if the width of the support is less than 1/12 of the clear span. However, here the clear span is equal to 4.54, student. Therefore 4.54 divided by 12 I do have 0.378. However, the width of the support is assuming 230 mm beams, 230 mm, right. Therefore the 230 mm is less than this L by 12, therefore 378. Hence now code says that then the clear span of the effective span shall be as per this class 22.2.8 itself, means as per that of the simply supported beam only. Now the code says effective span of a member shall that is not built integrally with its support shall be taken as a clear span plus effective depth of slab or beam or center to center of the support, whichever is less. Therefore once I examine this, now let us substitute the numeric values, student, right. Therefore just recall that formula. Hence the minimum of these two is equal to clear span is equal to 3540 in the small span direction, and plus B 230 mm, assuming 230 mm width of the beam as 230 mm, right. Now that is 230 mm, right. Then that are clear span 3540 plus the depth of this slab. That effective depth of the slab is 106 mm, right. 106 mm. Previously it was the width of the width of the beam 230 mm, 230 mm, or out of these two, which is minimum. Therefore now we'll get the second one as the minimum, therefore it works out Lx is equal to 3646 mm. And similarly the effective span in the length direction will also work out in a similar fashion as 4540 plus 106, or say it is 4646 mm. Right now I'll get the ratio of this longer span to shorter span. It works out say 1.274, which is less than 2. Therefore as it is less than 2, obviously the distribution of the load on the slab is biaxial. Therefore it bends simultaneously in both the directions, right? Now that is the biaxial bending of the plate will occur, or that of the slab will occur like this, right? Biaxial bending, or it is two-way bending, right? Therefore now once we examine that, now what I'll do is now I'll go to this class IS 456 class D 1.1, is table 26, page number 91. Let us revisit this page, student, page number 91. 91. Now I am there in this page number 191, where I do have this table bending moment coefficients for rectangular panels supported on 4 sides with provision for torsion at corners, right? Now I do have these edge conditions, 3 edges discontinuous, whereas one short edge continuous. Now you can see that almost here 3.54 internal, right, and 4.54 and 4.54, these 3 are discontinuous, whereas this is a continuous edge because it is supported on the beam like this, and it is continuous over this support, therefore there is this case 8 I'll take. Therefore what are the negative bending moment coefficient at continuous support? No, nothing. Whereas in the long span direction it is given as 0.057. Now similarly the positive bending moment coefficient at mid span I do have this value alpha by this Ly by Lx is equal to 1.2 and 1.3. I'm just noting down that 0.059 and 0.065 along this x direction, as well as short span direction, as well as that of the y direction, long span direction, as 0.043. Now I'll interpolate. Therefore you know how to interpolate, student. I have just noted down from the table 1.2 and 1.3. Therefore I require for a value of 1.274. therefore now upon interpolation I'll get this positive bending moment coefficient as 1.274. I'm just recalling that value. I'm recalling this value. I'm interpolating. Upon interpolation. I got this value as 0.063 upon interpolation between these two. Whereas alpha y in the long span direction it is given as 0.043. Therefore I have noted down these coefficients from this table 26 of IS 456. Then I'll calculate the loads. Coming on the slab, right? Coming onto this slab, right? Therefore these are the different loads, student. Right? Now I'll assume that though there is no staircase provided, now we'll assume that a ladder can be provided and people can access to the top of this terrace floor, right? With that assumption I will simply calculate the different loads, right? Therefore these are the dead loads. The dead load of the slab from IS 875 part 1, dead load intensity of the RCC is 25 kN per meter cube. Therefore that multiplied by 0.125, it works out 3.125 kN per meter square. Next one is the floor finishes. Assuming 25 mm floor finishes, I do have the unit weight of these floor finishes, that of the PCC, assuming at the rate of 24 kN per meter cube, that multiplied by 0.025, it works out 0.6 kN per meter square. And also assume that 10 mm thick ceiling is done, the plastering is done to the ceiling. Therefore that multiplied by 0.01 multiplied by 24, it works out say 0.24. Now also what I have shown here is the parapet is provided, 0.9 meter height parapet, right? Therefore now even what we can do is that parapet load can also be taken as a UDL on the beam, and you can analyze, or alternatively what now I'm doing is I'm taking that is the total load along the periphery of this building, and I am assuming it to be uniformly distributed over the entire area, right? Whereas the previous one is more appropriate rather than that of this second assumption, right? Therefore, I am proceeding with this second assumption that the thickness of the brickwork there, that of the parapet is only 4.5 inch brickwork. Therefore, it is 0.0115. That multiplied by height, the height is equal to 0.9 meter. 0.9 meter, I do have the total peripheral length of this building. Let us see the outer dimensions of this building, student, right? What is the outer dimension? In the length direction, the total length is equal to 4.54 multiplied by there are 3 panels, right? And in between I do have 2 thicknesses of 0.23. Therefore, now it works out, say a value 14.08 is the outer to outer dimension. Similarly, in the width direction, it works out, say 3.54 plus 0.23. It works out, say 3.63. Therefore, I have these dimensions. Therefore, now I take the total length is nothing but the length plus breadth multiplied by 2. Therefore, I'll get the total peripheral length of the brick wall. And assuming this brick wall of density of the brickwork as 20 kN per meter cube. Therefore, that I am assuming that it is spread over an area of 14.08 multiplied by 3.68. Right, 3.68, right, outer total dimension. Therefore, it now works out 1.42 kN per meter square, student, right? And even I am assuming that plastering will be done plastering will be done like this. Even some artificial works will also be done. Therefore, now I'll add, say, 0.36 kN per meter square for that. Therefore, it now works out 1.78 or approximately 1.8 kN per meter square, right? This is one way of taking that load in the form of intensity of the load, or alternatively what you can do is directly take that load on the beams, on the longitudinal beams as well as that of the cross beams, right? That will be more appropriate, right? Either of the two is true. then I'll get all these are the different dead loads. These 4 dead loads. However, I'm assuming that the people can access this terrace floor by means of, though staircase is not provided, right? Or alternatively, at a later point, staircase may also be provided so that people can access, right? Therefore, with that assumption, I am taking that line load as, say, 2 kN per meter square, 2 kN per meter square, right? Therefore, now I'll add all these 1 plus 2, right? 3.125 plus 0.6 plus 0.24 plus 1.8 plus 0.2. It works out 7.78 or approximately 8 kN per meter square, which is unfactored load. Therefore, now multiple factor of safety, but dead load as 1.5. Therefore, that 1.5 multiplied by 8, it works out 12 kN per meter square. Now, once I get this factor load, now I'll calculate the bending moments, right? Therefore, the positive bending moment are along the short span. Is equal to alpha x equal to WLX square. As per this code specification, student, just now we have seen this, right? There is the formula, right? WX, right? Mx is equal to alpha x equal to WLX square. My is equal to alpha y multiplied by WLY square. Therefore, substituting the different input values, right? And now I have mx is equal to 0.063 multiplied by 12 is the factor load multiplied by 3.646. Just now we have seen the effective span whole square, right? That works out, say, approximately 10. This has 10.05 kN/meter. Similarly, in the long span direction, it works out, say, 6.86 kN/meter. 6.86 kN/meter. Once I get this bending moment, student, what I will do is I'll go for the checking for the depth. There is a first submitting, right? Therefore, from Flexure point of view, whether the depth provided, is it okay or not? Right? Is it okay or not? For this slab, is it okay? Right? Is it okay or not? Right? Therefore, now I'll say that we already know from this IS 456 class G.1.1C, page number 96, right? Or if I go to SP 16 1980, table C, that of the page number 10. Let us go to the page number 10, student. That of the SP6, SP16, right? Table C, page number 10. Table, right? This is our table C, page number 10. We do have IS, this Fi is equal to 500. Therefore, MU lim divided by FCK BD square is equal to 0.133. Similarly, PT lim Fi divided by FCK is equal to 18.87. You can make a note of these values, right? Once I note down that I am saying that yes, MU is equal to 0.133 FCK BD square. Therefore, the depth required is equal to how much, right? I already know what is this value of MU, whereas MU in the short span direction is governing the design rate, which is 10.05 kilonewton meter. That divided by 0.133 multiplied by 20 FCK multiplied by. Now always the slabs will be designed per 1 unit length. Therefore, B is equal to 1 meter or 1000 mm. Please make note of this, student, right? Therefore, 1 meter means 1000 mm. Now it works out the depth required is equal to 60.43. However, the depth provided is already 106 mm. Therefore, okay. First comment, it is okay, and the second comment is that the depth required is much less than the depth provided, means more concrete is provided. Therefore, it is under reinforced concrete. Means the stresses, the more concrete is available. Therefore, the stresses in concrete will not reach the permissible stresses, but the steel will reach its permissible stresses first. Therefore, that is how the steel will reach the permissible stresses. Once we know this, then I can go to this class G.1.1b, page number 96, right? Therefore, that is how page number 96. Let me move to that page number 96 of IS 456, student, right? That is how that page number 96. 96 means now I do have that this page number 96 where I do have this formula as say. This formula as this is applicable for movement of resistance of rectangular and T sections, right? Where I do have this rectangular section where this depth of the neutral axis is given by XU by D 0.87 FI AST divided by 0.36 FCK BD, and MU, the movement, is equal to 0.87 FI AST D minus 1 minus FI AST divided by FCK BD. And MU lim is equal to 0.36 XU max by D 1 minus 0.42 XU max by D FCK BD square. Just using this formula, just now we got MU lim is equal to 0.133. Therefore, however, this using B, MU is in terms of a quadratic equation in terms of AST. Either you solving that, now I'll get what is the area of the steel required. Therefore, what is the area of the steel required? Therefore, now I'll use that equation, or alternatively I can use the other equation as AST is equal to 0.5 FCK divided by FI multiplied by 1 minus square root of 1 minus 4.6 MU divided by FCK BD square, that whole multiplied by BD. Either of the two equations will give the area of the steel is equal to how much. Now I'm calculating first in the short span direction. First the reinforcement in the short span direction, right? Therefore, for 10.05 kilonewton meter means 10⁻⁶ Newton mm, right? I'll give the different inputs, student, right? What is the effective depth and others, right? FCK 20 and B is equal to 1 meter, so on and so forth. Then I'll get the area of the steel required in X direction as 231 mm square. Similarly, now if I substitute MU is equal to 6.86 kilonewton meter in the long span direction, then I'll get correspondingly the area required. Area required is equal to 155 mm square respectively. However, this I need to check using this codal specification. The minimum steel in the slabs should be 0.12% of the gross cross-sectional area, if at all it is FE HYSD rods. Therefore, I do have HYSD of FE 500 grade steel. Therefore, 0.12 multiplied by gross cross-sectional area, 1000 multiplied by 125, it works out 150 mm square. But what I got from the flexure point of view is 231 in short span direction as well as main span direction. Therefore, this AST minimum will not govern, but the design will be governed by the flexure in short span direction as well as the long span direction. Both 231 and 155 will govern. Let us say if this value is equal to either of the value is less than 150, then area of the minimum steel will govern the design, not that, right? I hope you understood how the main steel will be fixed, student, right? Now I'm taking I'm assuming 8 mm dia, that already assumption made. Therefore, the spacing of the 8 mm dia bars required is equal to how much? Is equal to that small AST pi by 4 8 square 50.2 divided by capital AST. Area of the steel required. Area of the steel required. Just now we got 231. Therefore, in the short span direction for 231, I'll get say the spacing required is equal to 217 mm. 217 mm, student, right? Now let us see if I get 217 mm. Now let me also go with the other checks, right, at a quicker pace, right? Therefore, once I get that, now I'll say to start with what I am assuming, that I am assuming these 8 mm dia at 8 mm dia at 200 mm center to center. Therefore, now I can calculate what is the percentage of the steel provided. Now let us say it is approximately, right, 0.28 percentage. Therefore, now I'll make a check for deflection. Therefore, for making a check for the deflection, student, what now I'll do is right, I'm assuming that these 8 mm dia are provided at 150 mm center to center. Therefore, AST provided is equal to 300 mm square. Therefore, this FS is equal to 0.58 multiplied by AST required by STAAD.Pro, right? AST required is equal to some 231 divided by STAAD.Pro is equal to 300. Therefore, now I'll get this approximately 248.3 Newton per mm square. Right? Whereas from this page number 38, now I do have the modification factor for this tension steel 0.28 percentage from IS 456. It is equal to 1.5. Whereas it is a continuous slab. Therefore, the basic value is 26 multiplied by this 1.5. Modification factor for the tension steel, it now works out 39. Therefore, L by D permissible is equal to that L by D actual is equal to 3646 divided by 106. It is 34.3 is actual value, whereas what is permitted is 39. Therefore, 34.3 is less than 39. Hence, it is the provided depth. The provided depth is, as well as the provided steel, is okay from deflection point of view. Whereas for cantilever beams, the basic value is equal to 7, and for the simply supported beams or slabs, it is basic L by D value is equal to 20. You are already aware of, right? Once I do that, now let me go quickly to the top. The check for the shear, student. Now already I know what is that percentage of the percentage of the steel provided, right? 100 AST by BD is equal to it worked out 0.28 by assuming by providing a steel of 300 mm square, right? Therefore, from that table 19 of IS 456, now interpolate. Therefore, for tau c is equal to 0.25, for tau c is equal to 0.5, I do have the PT is equal to 0.25 and PT is equal to 0.5. I do have the tau c value as 0.36 and 0.48. Therefore, for 0.28 PT, this tau c is equal to how much? That now works out around 0.374. Whereas what is the actual nominal shear stress? Nominal shear stress is like this: is the shear force, the factor shear force is equal to W multiplied by LE by 2, whereas WU is the short span direction 3.646 multiplied by factor load 12 divided by 2 means 21.96. Therefore, if I divide that with B and D, now I'll get 0.2 Newton per mm square is a nominal shear stress, whereas I have a design permissible shear stress of 0.374. Therefore, even here, because the thickness of the slab is 150 mm, then multiplication factor for the solid slabs is 1.3. Therefore, the permissible shear stress is K multiplied by tau c, not just simply tau c. Therefore, 1.3 multiplied by 0.374, it works out 0.486 is permissible, whereas the actual shear stress is just a value of 0.2. Obviously, please make a note that the shear stress will not be a critical check for the slabs. Right? Once I see this, now let me quickly go to the top, the design of this slab using the Excel sheets. So far, I have shown the manual calculation, design of the manual calculations, right, of the slab. Now I'll show the same using Excel sheets, right? Therefore, this is my Excel sheet for the design of the slabs, wherein Fi is equal to 500 and FCK is equal to 20, and clear cover is assumed as 15 mm, and this long span, clear long span direction span is equal to 4.54, and short span clear dimension is equal to 3.54, and I'm assuming the width of the beam as say 230 mm, and the slab thickness as 125 mm. Therefore now I'll calculate using this Excel spreadsheet what is the dead load. Dead load is equal to that 0.125 multiplied by 25. Just now we have calculated it works out 3.125, and floor finishes I have just explained, right? I'm adding 1.075 and partition loads, right? That of the brickwork. I already explained it. Actually, that may be thrown either as a UDL also, but I have considered that as thrown on the slab as 1.8 kilonewton per meter square, and live load is equal to 2. Therefore, all put together it works out 8 kilonewton per meter square, and now even I'll calculate what is the effective length in the long span as well as short span directions, right? And I'll get what is that alpha is equal to LY by LX 1.293. Once I get this, I'll go to this IS 456 class D.1.1. Just now we have seen the table 26, page number 91. Whereas I do have these edge conditions, one short edge continuous, like this you can see, right? There are the 9 edge conditions, right? Therefore now the appropriate edge condition is one short edge discontinuous, whereas the other 3 edges are continuous. These 3 other edges are continuous. So this is the edge condition 8 from the table. Now I'll get the coefficients, right? That of the positive bending moment coefficient along the short span direction as 0.071, and along the long span direction it is 0.044, and that of the negative coefficients, negative bending moment coefficient along the support as 0.058. Therefore for these are the bending moments I am calculating. And what is that area of the steel required? Is now respectively 150, 226, 201, 150 respectively. By assuming 8 mm dia, what is the spacing required? 335, 222 and 250 and 335 respectively. Therefore once I get that, now either you can provide 8 mm dia 200 center to center through and through in both the directions, right? Now once I do that, now let me do the check for the deflection also, right? As per this IS 456 class 23.2, page number 37, just now we have said FS we have calculated 261 Newton per meter square, and PT we have calculated because this much of steel is already provided 8 dia 200, therefore it works out 0.24, and therefore what is that modification factor for this tension steel? It now works out 1.48 from that IS 456 graph, right? Therefore what is the depth required is now 88.2, whereas the depth provided is equal to 106 mm. Therefore required is 88.8 is less than 106. Therefore it is okay, right? That is how the design of one panel wherein one short edge is discontinuous. Whereas even now let us see what is the design of the other panel, right? Even there is another panel student, right? So far I have done the design of this panel student, right? Using manual calculation as well as I have shown using the Excel sheet, right? Even let us see the difference, how much of difference is there from that of the Excel sheet, right? Even right here from Excel sheet I am getting this MX instead of 10.05 I am getting that 9.88. Even in y direction I am getting 6.09. hardly there is small error. Therefore my Excel sheet is perfect, right? Even now I am getting the steel from this Excel sheet, right? Whereas manually I have calculated I got 231 along the small span direction, whereas from this Excel sheet I am getting 226 mm square, right? That is how I am getting this 226 mm square. Therefore it is okay. It is means my Excel sheet is proven. It is a proven spreadsheet, right? Therefore once I do that, what I'll do is I'll try to even other checks are also okay, right? That is how right, other even it is okay in this deflection check also, right? Once it is okay, now I'll do the design of the interior, this second panel 2 of this slab, right? Wherein here you can see that this edge is discontinuous, as well as this two long edges are discontinuous, whereas the 2 short edges are continuous. Therefore using that, now let us do using Excel sheet. Now I will not do manually, right? That is advantage of using the Excel spreadsheet student, right? Now I'll do that design, whereas the other inputs are same, do, right? No change, but only here you please see that the two edges, two long edges are discontinuous. This edge condition 6 from this table 26 of page number 91, for which I have just noted down. The Excel sheet program is written in such fashion that it will automatically recall, right, the coefficients, right, 0.0, 0.064, 0.045 and 0.034. Correspondingly, the movements are given by this, and the area of the steel required is 150, 204, 155, 150, whereas the 8 mm dia spacing required is 335, 246, 324 and 335 respectively, but I am providing 8 mm dia 200 center to center because I already provided in the just left span also the same reinforcement. Now let us check, is it okay from the deflection point of view? Yes. Now it is saying that the depth required is 77.9 mm, whereas the depth provided is equal to 106. It is okay. It is okay. Now let us check, student, if I change the edge condition, right, or let us say if I decrease the depth of this slab drastically, let us say I am just decreasing this by 100 mm. You can see that of the first condition wherein one short edge continuous, there instead of overall depth as 125 mm, I have just changed to 100 mm thick, right? Whereas now code is saying that even obviously the design will change, right? You require more steel also, therefore major steel 180. Even let us say if I just provide same 180 everywhere, right? However, even despite of that, now I am providing same 180, but now code is saying that the depth required is equal to 113.6, whereas the depth provided is equal to 81. That is not acceptable from deflection point of view. It may be okay from flexure point of view, but it is not acceptable from the deflection point of view. Therefore, if it is not okay from deflection point of view, means the limit state of serviceability in that criteria, it will fail. It will not fail in limit state of strength, but it will fail in limit state of serviceability criteria. Therefore, not acceptable. Therefore, now I need to revise. Therefore, I'll revise that assuming once again same 125. Therefore, if I am saying 125, then it is okay. Yes, 88.8 is required. 106 is provided. Therefore, okay. That is how the advantage of using this Excel sheet, student. Right? I hope you understood how we have done the design of the slab at a quicker pace using the Excel sheet, using Excel sheets. Right? In the next class onwards, we will only use the Excel sheets only, right? We will not go for the manual calculation, student, right? You please make a note of, right? Once I do that, now I'll move to the top, the analysis and designs of the beams, right? Analysis and designs of the beams. I hope you are understanding these discussions. So far we have analyzed the slabs resting on the beams, right? Now I'm analyzing these beams, right? And I'll design, right? Therefore, now I'm assuming that let us assume the size of the column, as 230 mm by 375 mm, and the top now I'll get even what is the effective length of these beams, B1, B2, B3, right, B4, B5, B6, B7, B8, B9, B10, right? Whereas B1, B2, B3 is continuous beam, whereas B4, B5, B6 is also a 3-span continuous, whereas B7 and B10 are the exterior beams, whereas B8, B9 are interior beams, right? Therefore, once I say that, now what I'll do is I'll calculate what is the the span of these beams, the beams, right? B1, B2, B3. Therefore, now I'll say that is equal to 4.54 plus 0.5. Therefore, that now works out say 5.04, or alternatively what I can say is 4.54 plus 0.375, because my column size is equal to 0.375. Therefore, 4.54, because that is a clear plus the column dimension in the span direction is equal to 0.375. If I add that, now I'll get here half, even at the other end half, right? That is a 375 by 2, 375 by 2. That works out 375. The first result is equal to 4.915. Therefore, this effective span of this beam is equal to 4.915 student. And similarly, that of the beam these exterior beams are interior beams, right? B7, B8, B9, B10 appropriately respectively are 3.54 plus 0.4 are, now I am assuming the column size as 0.23, therefore 3.54 plus 0.23, it is equal to 3.77. 3.77 is the effective span of these beams. Once I get the spans of these beams, then I will go for the analysis, student, right? Now this is how I will initiate the analysis of these 3 span continuous beams, either B1, B2, B3 or B4, B5, B6 respectively, right? Now I am assuming the size of the beam as 230 mm width by 525 mm. 525 mm from the past experience, right? Past experience. Therefore, assuming this, now I'll get the dead load of the beam as say 0.23 multiplied by 0.55 multiplied by 25. So 25. It works out say 3.02 kilonewton per meter. And if I multiply with 1.5, then I'll get the factored dead load is equal to 4.52 kilonewton per meter, right? And now I'll calculate this ratio as beta is equal to the ratio of this long span to short span. Even previously also calculated, right? It worked out to 1.23. Once I get this, because I am trying to do this calculation of the loads manually, therefore now I'll go to that of the SP24 student. I'll take the help of the SP24, right? Now before I go for the manual calculation, student, now code says that this SP, I am there in SP24 1983, right? Now code says that the substitute frame, right, the may be used for manual calculations, right, where it is subjected to where the idealization does not apply, whereas the substitute frame is not applicable when it is subjected to lateral loads and is applicable to purpose of the analysis under gravity loads only. Here in this problem, in today's problem, that of the ground floor, I am not assuming any lateral loads. Please make note, student. Therefore, I can make use of this substitute frame method, right? For elaborate discussion on this substitute frame method, please revisit our previous video on analysis and design of RCC substitute frame using STAAD.Pro, previous video, student. Then there you elaborately discussed how a substitute frame should be considered and how analysis should be done, right? I hope you watched that video, right? Then you understand how the substitute frame method can be used for analysis, for manual analysis subjected to gravity loads only, right? Therefore, that is what either you take the substitute frame, right, like this, or that of either this option, right, say two columns and continuous, or these 2 columns continuous and this beam continuous there on one side, so on, and all these permutation combinations, right? Once you take this, right, for manual calculation, then you can do how much of load is coming on to each of these beams. Now calculate that using this formula, student. Now loads on the supporting beams from the same SP24. Now code says that load on the short beam is equal to WLX square by 4, right? Where L is the length of the short span and L is the length of the long span. Therefore, on the short span, WLX by 3, and the long span it can be taken as WLX by 6 multiplied by 3 minus LX by LY whole square. Or alternatively, I can write the same like this, right? Therefore, on the short span, the triangular load is equal to the equivalent UDL for bending moment WEB, right, is equal to K1 multiplied by WLX by 2, whereas that K1 is equal to 2 by 3. Therefore, it is equal to WLX by 3 finally, right? Similarly, for the analysis of getting the shear forces and reactions, then the equivalent UDL for this triangular load should be taken as WES to the subscript S, right, which is equal to K2 WLX by 2, means where K2 is equal to 1 by 2, means is equal to WLX by 4, right? Or even I do have, right, like this. Actually the loads are distributed like this, right, on the beam, triangular load, as well as on this long beam, right? I do have the loads are distributed at 45-degree angle, right? Now I do have a line 45 degree, both are meeting, right? Therefore, meeting that of this central longitudinal axis of this beam B3. Therefore, this triangular load will go on to this beam B3. This triangular load will go to on this beam B3, right? Whereas this trapezoidal load trapezoidal load will go to this B1, whereas this trapezoidal load will go to this B2 from this panel. Similarly, from the other panel also get another trapezoidal load. Therefore, there are the two trapezoidal loads coming onto this interior beam, like this, right? Trapezoidal load as well as the triangular loads, right? Therefore, what are these equivalent loads? I am just calculating, right, from SP24, right? Therefore, for the trapezoidal load, that equivalent load for the bending is given by WLX by 2 1 minus 3 beta square, or it is equal to K1 multiplied to WLX by 2, where K1 is equal to 1 minus 1 by 3 beta square. Whereas if you want to analyze for the shear, it is given by WLX by 2 1 multiplied to 1 minus 1 by 2 beta, or K2 multiplied to WLX by 2, where K2 is equal to 1 minus 1 divided by 2 beta, 1 divided by 2 beta, right? Once I see this, now what I'll do is I'll substitute into these, right? Therefore, I'm just doing that. Hence, from this page number 57 of SP24, I'll substitute. I do have already load WU is equal to 12 and LX is equal to 3.77, just now calculated, right, in the previous subheading. Now I'll get 17.64 is the load, from manual calculation. For bending analysis, for the bending student, right, like that, for analysis for the getting the shear force and reactions, it is quite different. Please see that, right? Therefore, now the total UDL is equal to this 17.04 plus this 4.54. It now works out at 22.15. Right, equivalent UDL, right, on these continuous beams, B1, B2, B3, or B4, B5, B6, right. Similarly, let us see what is that load on these exterior beams B7 and B10 respectively. Therefore, if I now I'll change the assumption, right, of assuming the sizes of the beams of these beams as 230 by 425, and I'll get the dead load as say 2.44 kilonewton per meter, and this multiplied by 1.5 gives 3.6 kilonewton per meter. Whereas on this just now we have seen the triangular load will come. Therefore, that is equal to W U LX by 3, whereas LX is equal to 3.77 divided by 3, and W is equal to WU is nothing but 15.08 plus 3.66. Right, that works out 18.74. That right, 18.74, right? No, sorry, WU is that of the factored load onto the slab, that is equal to 12 multiplied to 3.77, right? 3.77 now divided by 3, it is now giving 15.08 kilonewton per meter. Therefore, that plus sulfate 3.66. Now I am getting that total load is equal to 18.74 kilonewton per meter, right? And that is how the total load, student, right? Now that of the triangular load, right? Now once I get this, what I'll do is, right, now I'll go to that of the calculation of movements on these beams, on these continuous beams, right? Even similarly, I'll calculate that on that of the interior beams also, right? This is two times that value, right? Now I'll analyze the beams, these continuous beams B1, 2, 3 or B4, 5, 6. Therefore, I am there in that analysis, student, manual analysis, that of the beams 1, 2, 3, 4, 5, 6, right? Wherein to start with, I am just taking only that of the interior span, right? This span alone, right? For just manual calculation, right? Or this span, right? Or alternatively, what you can do is you can take that of these three spans, continual spans, and you can analyze using the substitute frame method, right? Now I'm doing this optional, right? I'm assuming that this is continuous on either end, right? And I'm analyzing like this, right? Therefore, it is subjected to a load. Load is already calculated 22.15 kilonewton per meter, student. Therefore, assuming both ends to be fixed, right? Now I'll have the fixed end moment is equal to W square by 12. Now, whereas this long span is equal to effective span is equal to 4.625 whole square divided by 12. It now works out as 39.48 kilonewton meter. Whereas that of at the center now we'll get W square by 24, which is equal to 19.74. This value 19.74, by assuming the both ends to be fixed. However, Similarly, if I analyze for the shear forces, now I'll get the shear force is nothing but the total load 22.15 multiplied with this 4.625 divided by 2, it works out 51.22 on either support, right? Either of these two supports, right? Similarly, now let me analyze that of these exterior beams, right? Because there is only one span, therefore I'll assume that both are fixed at both the ends because of the stiffness of the beams at the other ends, because those beams are of a higher size than that of these 7th and 8th beam sizes, right? Therefore I can assume that it is fixed on either side. Therefore, with that assumption, if I calculate what is that the bending moment, that fixed end moment at the support is equal to W square by 12, whereas W is equal to 18.74 multiplied by 3.77 whole square divided by 12. It works out 22.19, whereas at the center W square by 24, it is 11.09 kilonewton meter. That is how the bending moment variation from 22.19 to 11.09 on the exterior beams. Similarly, I'll go to the top, the interior beam side. Now I'm assuming the size of the interior beams as 230 by 525 mm, right? Therefore, what is the dead load of this beam is equal to 3.02 kilonewton per meter. That multiplied by 1.5, it works out 4.52. Therefore, that 4.52. However, the loads are coming from trapezoidals, two trapezoidals. Therefore, 2 multiplied by this WLX by 3, right, is equal to 30.06, right? 2 multiplied by 15.08. This value is equal to, we already calculated in the previous subheading that for beam 7 and 8, we have calculated as 15.08. Therefore, 2 multiplied by 15.08, 30.16. Therefore, the total load is equal to this 30.14 plus 4.52. It works out 34.68. This much of load. Therefore, these beams are fixed at both the ends, right? Therefore, the fixed end moment is equal to W square by 12. It is 41.07 kilonewton meter, whereas at the center W square by 24, 20.53 kilonewton meter, and the reactions are the support reactions are 65.737 on either end, right? This is how I've just considered only in the short span direction. Only one span is there, one span only I have considered. But what I have done is out of these 3 spans, I have just considered only single span. That is how I have done analysis, right? Even now you can do 3 span continuous beam also, or alternatively you can go to the shear force and bending moment coefficients that are given in IS 456, and you can do analysis of these 3 span continuous beam. Therefore, either of the 3 will give the bending moments in these beams, right? Therefore, I have to have these input values, right? Now, once I have these input values, now what I'll do is I'll just initiate the design. Let me see the design at a quicker pace, student. In the previous class you all seen this elaborately, therefore I'll just do that at a quicker pace. Therefore, now I have to have for the design of the beam, for the design of these continuous beams 1, 2, 3 or 4, 5, 6, the dead load is already calculated. The size is 230 by 525, and I'm assuming that 25 mm is the effective cover, or actually the clear cover itself is 25, and assume some 60 mm diabar, right? Therefore, even 500 minus 8 means some 492 mm is the effective depth, or you may say 25 mm is the effective depth. Then in which as the effective cover, then my effective depth is equal to 500 as appropriate, right? You make an assumption as appropriately and calculate what is the effective depth provided, right? Therefore, once I get that effective depth, now I'll get I already know after analysis I got moment mu is equal to 39.48, say approximately 40 kilonewton meter. But we already know for this Fe 550 grades 500 grade steel, mu limit is equal to 0.133 FCK BD square, whereas B is equal to 0.23, and D effective depth either 500 or 492 mm square. Therefore, that gives the limiting moment of resistance of that beam is equal to 152.9, whereas what is I do have that factored movement is only just 40, which is much less than this 152. Therefore, that indicates that the section is under-reinforced section. Once the section is under-reinforced section, then as per this page number 96 of IS 456, just now we already visited during the design of the slab theorem. Now we know this formula: mu is equal to 0.87 FI/AST multiplied by D, 1 minus FI/AST divided by FCK BD. Therefore, substituting into that, now I'll get for this movement of 40 kilonewton meter, I do have area required is equal to approximately 189 mm square, student, 189.4 mm square, right, for 39.48. Here what is now shown is for 40 kilonewton meter, it is 191, but I have calculated for 39.48. actual bending moment, it is approximately 189. There is no much change, right? See, now once I get this, even similarly in the other direction we got a bending moment of 19.274, student. Therefore, for that, what is that area of the steel required? Using the same formula, even the section is now under reinforced section, because mu is much less than mu limb, because the depth required depth provided is much greater than that of the depth required. Our depth required is much less than that of the depth provided. Therefore, the section is under reinforced section. Hence, in the other direction, in the sorry, not in the other direction, at the center for positive bending moment, of 19.74, I require just 92.93 mm square, whereas for the negative bending moment I require approximately 190 mm square. Therefore, these are my the areas of the main steel. But however, I'll check this from the minimum area of the steel point of view, as per this class of IS 456, which states that A naught divided by BD is equal to 0.85 multiplied by divided by F5, substituting which, now I'll get approximately minimum tension steel area is equal to 196 mm square. But what I got in the previous discussion is 189, is also much less than this AST minimum in at support as well as at the midspan. 93 is also much less than this 196. Therefore, that will not govern the design, but this minimum tension steel will govern the design. Therefore, assuming either say 12 mm dia bars, right, 12 mm dia bars, I'll get say approximately some 1 point odd value, or say you can provide two 12 mm dia bars, therefore which will furnish 236 mm square, both as compression steel as well as that of the tension steel, right? That is the compression steel in the top as well as the tension steel at the bottom, right? Both respectively for these longitudinal beams, right? Similarly, for that of the two edge beams, that of the exterior beams, beam number 7 and 10, where the size is equal to 230 by 425, student, right? Even we are analyzed and we got mu is equal to 22.19, say approximately 23 mm square. Therefore, what is the limiting moment of resistance? 0.133 FCK, 20 multiplied by 230 multiplied by 425. It is 110.5 kilonewton meter. Therefore, this also states that the section is under reinforced. Therefore, once the section is under reinforced, now what I'll do is I'll calculate the area of the steel required. Therefore, I'm now getting the area of the steel required for this 22.19. I'm getting 137.3. However, this is much less than that AST minimum. Just now we have seen that, which is equal to 150, approximately 150 square, 156 mm square. Therefore, this 137 from Flexure will not govern the design, but AST minimum tension steel will govern the design, right? Even in the other direction, for the positive bending moment of 11.09, I require 102 mm square, but this is much less than 156 mm square. Therefore, it is not acceptable. Therefore, here also for this 7 and 10, 156 is the minimum steel required. Therefore, you provide 212 mm as a compression as well as tension steel. Here also no change, manual change, right? Whereas once I do the design for the main steel for the 3-span continuous as well as 2-span continuous beams we have seen, student. Now I'll initiate the check for the shear. I hope, student, you are understanding the discussions we are there in the next subheading as check for the shear for the main beams, right? That are the 3-span continuous beams 1, 2, 3 or 4, 5, 6, right? Therefore, assuming 8 mm dia 2-legged vertical stirrups, right? What is that? Spacing, the spacing required for these stirrups is equal to 0.87 Fi ASV divided by 0.4 B. It works out, say, approximately 394 mm. However, 394 mm. However, I do have that minimum stirrups spacing also, right? Minimum stirrups spacing, right? This is what from the minimum ASV by BSV. ASV by BSV is equal to 0.4 Fi divided by 0.87 Fi. This is the minimum spacing. From minimum stirrup spacing point of view, I got 394, right? Whereas here the check for shear is now I'll do, right? And I'll check whether the minimum shear reinforcement is required or that of the design shear force is required. Therefore, now what I'll do is I'll calculate the shear force, right, for the main beam. We already calculated in the previous subheading. It worked out 51.22 for the 3-span continuous 1, 2, 3 beams, right? 51.22 because it is 22.15 multiplied to 4.65 divided by 2. However, this 22.15 is for the bending. Even I have shown the equivalent load for the shear. Even now you can substitute that one, wherein you may get slightly less value, right? Nevertheless, I am proceeding with this, right? For this manual calculation. Therefore, the nominal shear stress now works out for this 3-span continuous beam 0.44. However, we already assumed that either 212 mm will furnish 226, or if I provide 312 mm, let us say I am assuming I am providing 312 mm, therefore 339. If I am providing 339, then AST is equal to 339 divided by what is that percentage of the steel. Therefore, 339 divided by area of this cross section of the beam. It works out 0.29. Therefore, from the table 9 of IS 456, right? Now I'll interpolate. What is that? For 0.25, I have to have a value as well as the value is also available for the 0.5. Therefore, for this intermediate value, I'll calculate what is that design shear stress. Therefore, the design shear stress will now work out a result given by this value. Therefore, now one moment, friend, right? Therefore, upon interpolation, I'll get this for 0.29 is equal to how much, right? I'm getting this result as say a value given by one moment, right? Given by this, right? Yes, given by this, right? Therefore, once I interpolate that, now I'll get this result, right? Therefore, I'm getting this result as 0.5 Newton per mm square. Therefore, now I can say that the nominal shear stress tau is 0.44 is much less than this design shear stress, right? Therefore, it is much less than, means we need to only check with respect to the nominal shear stress. Design shear stirrups are not required, or alternatively, or we can say that no design is required from shear point of view. But however, code says that if that is not that case, minimum shear reinforcement should be provided as per this code specification. ASV by BSV should be greater than or equal to 0.4 divided by 0.87 Fi. Therefore, now I'll calculate what is the spacing of this 8 mm dia 2-legged vertical stirrups. It now works out, say, 394 because 2 multiplied by 50.2 is the area of one leg. 8 mm dia leg is 50.2, right? Now that works out, say, 394. Therefore, that is how I got 394 is the spacing. However, even I do have the maximum spacing criteria, right, from the same code specification, right? For the vertical stirrups, right, 0.75 D. Here I do have D is equal to 500. Therefore, if I multiply, I'll get 375 R. In the worst case, not greater than 300 mm. Therefore, 300 mm will govern the design. Hence, provide 8 mm dia vertical stirrups at a spacing of 300 mm for the three span continuous beam. Similarly, if I do in a similar fashion for the edge beams 7 and 10, I'll get VU, which is self-explanatory, student. Now you can understand it. Therefore, VU is equal to that 35.32. Then nominal shear stress is equal to 0.38. Therefore, there also I am providing 3 12 mm dia bars. Therefore, 0.72. Hence, nominal design shear stress is equal to 0.71. However, that is much more than that of the 0.38. Therefore, no design is required for the shear reinforcement. However, nominal shear reinforcement should be provided at a rate of 8 mm dia 2-legged vertical stirrups at 394 mm. However, from maximum spacing point of view, just now we have seen 0.75D or 300 mm. However, 300 mm will govern the design. Hence, provide 8 mm dia 2-legged stirrups at a spacing of 300 mm center to center. 300 mm center to center, right? That is how the design of the exterior beams manually, right? Once we do that manually, the design of that exterior beam, student, now what I'll do is I'll come to that of the design of the columns, right? Before I go for the designs of these beams and columns using STAAD, right? However, now I'll go to that of these 4 interior columns, 2, 3, 6, 7, right? 4 interior columns. I do have 4 exterior columns, right? 1, 4, 5, 8 are the exterior columns. Therefore, I'll take the load on these exterior columns. Interior columns. Just now you analyzed, right? The reaction on the beams, we got 167.8 or approximately 170, right? 170. Therefore, now even what I have calculated, right? The bending moment after analysis of these 3 span continuous beam, I got 40 kilonewton meter, right? Actually, it is 40 on either side. Therefore, there is no bending moment on the column, right? On the column, because whatever that bending moment is there to the left is nullified by the right. Therefore, there is no bending moment on the column. However, that is equal to 0, but I am considering still that has 40 kilonewton meter, right? Now, similarly, that of from the transverse direction, right? Even we have analyzed the beam 8 and 9. Therefore, I do have a bending moment of 41 kilonewton meter, right? 41 kilonewton meter, right? Therefore, that will be resisted by the beam, by the column. Therefore, this is equal to 0, this is equal to 0, and this is equal to 41, right? However, minimum, however, we do have this minimum eccentricity of L by 500 plus D by 30. Therefore, from that, even that value should not less than 20 mm. Therefore, this PU 170 multiplied by 0.02. In any case, this value 0 cannot be taken, but this value shall be taken as 3.4 kilonewton meter about x-axis, whereas in the y direction it is 41, right? Like that, right? Now, this is the load on that of the 4 interior column, student, right? Likewise, let us move quickly to that of the what are the loads. I'll come to that of please make a note that here these 4 columns are subjected to uniaxial bending, because the bending from the continuous span, because this beam is continuous, right? Therefore, whatever the bending moment is there from to the left of this column is also there to the right of the column. Therefore, there is no bending moment from x direction. Only bending moment is there from the transverse beam number 8. Therefore, this column is subjected to uniaxial bending like this, right? Whereas the 4 edge columns, right? These 4 edge columns are subjected to biaxial bending, because they are now subjected to bending from x as well as that of the z directions respectively. Therefore, they are critical compared to that of this uniaxial bending. Therefore, I'll design those beams, not these uniaxial bending, student. I'll skip off this, right? Now, this is how the loads on to those 4 exterior column beam columns, right? 1, 4, 5, 8. numbered, right? Whereas their dimensions are 230 mm by 375 mm, and load coming on to that is 140. Just now we have seen that from continuous beam I am having at the end of this, right, the bending moment is equal to 40, negative bending moment 40, right? And also from the transverse direction, right, I do have the beam number B7, right? B7 we already analyzed, we got a negative bending moment of 23. Therefore that is how this bending moment is about one axis of this beam. This beam is acting in the x direction, if at all this is assumed as x direction, right? As well as from the transverse direction, right? 3-span continuous beam is applying the moment on this y-axis. Therefore that is how this column is subjected to biaxial bending, right? Therefore that is how this is critical compared to that of the previous column design, student, right? I hope you understand the design manual designs. However, we'll compare this with that of the STAAD later, right? Therefore I do have these two movements, and what is the effective length from IS 456 as per this class D, right? What the code says is that may be taken as 0.65. Even in the previous class we have seen that, right? Let me go to that class D, effective lengths, right? This is how that annex D student, where I do have in this annex D the effective lengths are given, right? Now code says that if both ends are fixed like this, right? Yeah, fine, right? In the previous class also we have discussed this elaborately. Please see this, right? Therefore I am assuming this condition effectively for general manual calculation. The code says that this table 28 gives the effective lengths of the compression members from IS 456. Now both the ends are effectively held in position and restrained against rotation in both at both the ends, because I am assuming that there are no lateral loads. I am not analyzing for the wind. Therefore that is my assumption. Therefore I am assuming that the column is effectively held in position and restrained against rotation, right? Restrained against rotation like this, right? It will not rotate. It will be rigid enough, right? That is what my assumption, right? Because no lateral loads are acting. If all lateral loads are acting, then accordingly you need to see the other either other code specifications, or if at all actual analysis is done, then you calculate what is that load onto that column, and you calculate what is that column stability index, and use calculate whether that is a sway frame or non-sway frame. Accordingly you use either this B1 and beta 2 to calculate for frame without sway using this figure 26, or with sway, frame with sway using this figure 27 as appropriate. In the previous class you have seen this discussion, so elaborately student, please revisit that. Therefore I am taking this effective length for manual calculation as 0.65. Therefore I have just noted down that, hence that is my effective length from the code multiplied by L. Actual length is equal to 3.2 meter. Now I get 2.08. And so what is the slenderness ratio? Lambda is equal to L effective by B. Now I get 2080 divided by 230 mm. It is 9.04, which is less than 12. Therefore, it is a short column. It is short column, not long column, right? However, even as per this code specification, right? As per this IS 456 page number 52, of IS 456, right? Page number 52, right? 52. I do have this page number 52, right? Wherein I do have the minimum eccentricity. Minimum eccentricity is given by this, right? L by 500 plus D by 30. Therefore, now upon substitution, L is equal to 3200 by 500 plus 375 divided by 30. It works out 18.9. However, it is much less than 20. However, if this value is less than 20, then at least you restrict it to or to 20 value at least, right? 20, right? Therefore now I'll take a 20, that 20 multiplied with this 140, right? I'll get 2.8 at least. Minimum from that minimum eccentricity, the minimum moment should be 140 multiplied by 0.02 means 2.8. However, my design bending moments 40 and 23 are much greater than that minimum movement 2.8. Therefore, I need not modify my movements. Whereas in the previous case, I have taken movement about x-axis from minimum eccentricity. Now I don't require that codal specification, right? Therefore, here I am just assuming that the percentage of the steel to be provided as 1.5% and the effective cover to the steel to the main steel that of this column is equal to 40 mm, right? Therefore d prime by d is equal to say it now works out 0.106. Therefore now I'll go to that of the SP16 chart number 48. Now let me calculate what is PU by FCK BD, right? PU is 140 and FCK is 20 and B and D 230 by 375. Now I'll get 0.08, not this 0.06 to 0.08. Similarly, this percentage of the steel, I was doing 1.5 divided by FCK is equal to 20. Even this works out 0.075. Therefore, from this SP16 chart number 48, let me revisit to that chart number 48 of SP16, right? Therefore, chart number 48, and then this chart number 45, right? Now I'll go to 48, yes, and then this chart number 48 student. Therefore, what now I'll do is I'll not this, right? Charts, right? Chart number 48. Just movement, right? Chart number 48, and then compression member design set, chart number 48. There I'll interpolate for this PU by FCK. For this PU by FCK, I'm assuming that the reinforcement is provided equally on four sides. Therefore, and Fi is equal to 200. Fi is equal to 500. Therefore, Fi is equal to 500. Therefore, this is my chart 47. Therefore, this is my chart 48, which is applicable to Fi is equal to 500, and chart 48 compression with bending rectangular section and with reinforcement provided equally on four sides, like this, right? Equally and which is applicable for Fi is equal to 500 with d prime by d is equal to 0.1. Just now we calculated the d prime by d is equal to 0.1. Therefore, now I do have PU by FCK BD is equal to 0.08, here roughly 0.08. And just now I got this P by FCK is equal to 0.075. Therefore, now I'll interpolate, and I'll get what is that like this, right? Now, what is that? Mu by FCK BD square. I'll interpolate and I'll get what is that? Mu by FCK BD square, like this, right? Mu by FCK BD square. Therefore, upon interpolation, I'll get this value as say. From this code as approximately say 0.15, right? Therefore, that 0.15 multiplied by FCK BD square, FCK multiplied by 230 multiplied by 375 whole square, it now works out about x-axis approximately 97 kilonewton meter, whereas I do have the actual bending moment about the major axis as 40 kilonewton. Therefore, it is okay. Similarly, about the minor axis, MUY divided by FCK BD square is approximately same 0.15. Therefore, MUY is equal to 0.15 multiplied by FCK multiplied by 230 whole square multiplied by 375. You know this calculation, student. Therefore, it works out say 58 kilonewton meter, but it is much more than that of the actual bending moment. Actual bending moment is equal to say just 23. Therefore, it is okay. This is okay. Therefore, it is okay in individual checks. And now let me go to that of once it is okay, then what I'll do is I'll now check the combined check also. Therefore, for which what I need to calculate is what is PUZ. Therefore, I'll go to this SP16 chart 63 from page number 148. Right there. From that I can calculate what is PUZ by AG. Now from this chart number 63. Therefore, this is our chart number 63, student, right? Chart number 63. Just a moment, right? Chart number 63. From this chart, I'll calculate what is that required, right? This is one procedure, or what alternatively what you can do. What you can do is even you can calculate manually also, right? That is how I do have what is this reinforcement 100 as by ag, right, for this corresponding value, right, for Fe 500 grade steel, right, Fe 500 grade steel, right. Now I'll go in the bottom direction, right, meeting this I do have FCK is equal to 20. Therefore what is that? PUZ divided by AG, Newton per mm square required. I've just noted down from this code specification, student. I'm getting that 14.5. Therefore PUZ is equal to that 14.5 multiplied by 230 multiplied by 375 divided by 10 to the power 3. It works out approximately 1251 kilonewton meter. Or alternatively, you can calculate using this formula also, 0.45 FCK AC plus 0.75 FI AS, or it gives either of the two will give the same result, no change, right. Therefore once I get that, now I'll calculate what is alpha n. That alpha n now works out approximately 0.112, student, right. PU 140 divided by this 12, just now we have calculated 1251 is approximately 0.112. Therefore from this class 39.6 of IS 456, from IS 456, now I do have from this class of page number 71. Let us revisit to that page number 71, student, right. 71 means I am there in this page number 71, right. This is a member subjected to combined axial load and biaxial bending from IS 456. The code says that MUX divided by MUX1 whole to the power alpha n is MUY divided by MUY1 whole to the power alpha n should be less than or equal to 1, where PUZ is given by 0.45 FCK multiplied by AC plus 0.75 FI multiplied by ASC, right, where PUZ should be 0.2 to 0.8 for alpha value varying from linearly from 1 to 2. Therefore now I'll interpolate from this. Therefore upon interpolation I'll get this result, right. Now I'll get this result as, say, a value 1 only, right, 1 only. I've just made a note of these inputs, student. Therefore let me calculate. Therefore I've just noted down those values as right, alpha n is equal to 1 and alpha n is equal to 2 for this one, whereas I do have alpha n is equal to 0.112. Actually even I need not interpolate because it is much less than 0.2. Therefore alpha n itself is 1, student. Therefore PU by PUZ is equal to 0.112. Therefore for that PU by PUZ is equal to 0.112. I do have alpha n is equal to 1. Therefore substituting in this formula, MUX actual bending moment about major axis is equal to 40 divided by that permissible, that moment of resistance using these sectional properties and as well as that of the steel provided 97 kilonewton whole to the power alpha n, means to the power 1 only, right, whole to the power alpha n. Whereas similarly in the y direction I do have 20 actual movement in y direction divided by 59 whole to the power 1. It is what called interaction between the two axes. It now works out, this is called interaction formula, student, 0.75, which is less than 1 unity, or sometimes it is called unity check, right. Therefore means that proposed 1.5% of the steel is okay, means therefore now I'll calculate what is the area of the steel required. 1.5 multiplied by 230 multiplied by 375, it is 1294 mm square. Therefore assuming 16 mm dia, each 16 mm dia will furnish 201 mm square. Therefore now I require number of rods required is equal to 1294 divided by 201. I require 6.43 or say because you are assumed equally provided on 4 sides, therefore provide 8 16 mm dia which furnish 1608 mm square, which is greater than that of that required value of 1294. That is how the design of the main shield, student. Once we complete the design of the main shield, then I'll go to this page number 49, class 26.5.3.2, right. 49. Let me go to that 49, right. 49. Therefore I am there in that page number 49. Therefore it gives the transverse reinforcement pitch pitch should be the least lateral dimension of the compression member 16 times the smallest diameter of the longitudinal reinforcement or 300 mm. Even the diameter of this lateral tie for the column shall not be less than 1/4 of the diameter, and the largest longitudinal diameter should not be less than 16 mm. However, we already assumed 16 mm. Therefore, now I'll calculate what is the diameter maximum of these two, right? 16 by 4 6 or 16 by 4 6. Therefore, I am assuming that 8 mm dia. However, I am assuming 8 mm dia. Therefore, 8 mm dia lateral ties I am assuming. Therefore, that is how I am calculating diameter 16 by 4 mm. Therefore, I am assuming 8 mm dia. Therefore, the pitch least lateral dimension is equal to 230. The second one is 16 multiplied by 16 mm dia assumed, right? 256 mm, and last one is 300 mm. Therefore, out of these three, 230 will govern the design. Hence, provide 8 mm dia ties at the rate of at a rate of 200 mm center to center. That is how the manual design of these columns, right? Once I do that, then I'll go to that of the design of the footings, right? Now let us see this design of the footing at a quicker pace, student. Then I'll go to that of the analysis and design by the STAAD, right? However, you already know the load onto the footing is 170 kilonewton, and I have not considered any bending moment, right? Actually, it is subjected to a bending moment. The footings at the exterior end is subjected to a bending moment of 23 as well as 40. Now I'll do that using Excel sheet. Now I'm showing just manual calculation without any bending moment, right? Therefore, that is how the dead load on the footing is assumed as 80. However, SBC is given as 200. Therefore, the total load is equal to 170 plus 80 is equal to 250 to 200, means it is 1.25 meter square. Therefore, I am assuming that length as 1.2 meter and breadth as 1 meter. Therefore, now 1.25 by 1 meter. Hence, I can provide length as 1.2 meter and breadth as 1 meter. Therefore, I am providing 1.2 meter whole square, right? That is how the dimensions provided. Now I calculate what is the net upward pressure. P0 is equal to 170 divided by actual area provided 1.2 divided by 1 meter, or it's approximately 141.6 kilonewton per meter square, which is much less than the permissible SBC of 200 kilonewton per meter square. Therefore, okay. Therefore, what is the factored load along x-axis as well as y-axis? It is P0 be 141.6 multiplied by 1, which is approximately 142 kilonewton per meter. Along y-axis, it is approximately 141.6 multiplied by 1.2 meter. 1.2 meter, right? Here it is 1.2 meter, and the transverse direction is 1 meter, right? Therefore, that is a rectangular footing is proposed. It works out 170 kilonewton per meter. Then I'll calculate what is the bending moment, right? The net bending moment is a cantilever bending moment, which is WL square by 2. Therefore, what is the cantilever along this 1 meter direction, right? As well as along this 1.2 meter direction, both, right? Along this length means along 1.2 meter direction. If I calculated, W is equal to 142 divided by 2 multiplied by this 1.2 minus 0.375 by 2 whole square, because that is the net cantilever from the face of the column. From the face of the column, there is a net cantilever subjected to this bending moment. Therefore, to the face of this column, which of bending moment is there, which is 12.08 along the length direction. Similarly, along the width direction, it works out say 12.6 kilonewton meter, right? Therefore, what is the depth required? D req is equal to square root of mu divided by 0.133 FCKB. However, even for the designers of the footing, we'll always consider this is a design of a slab. Therefore, akin to that of a design of a slab, therefore we'll consider B is equal to 1 meter, 1 unit meter. 1 meter. 1 meter means 1000 mm. Therefore, all the loads were calculated over 1 meter length. Hence, the depth required along this major cantilever projection direction as say as approximately 60 mm along the along the other transverse direction. Y direction as 57 mm. However, if I assume this effective depth as say 100 mm, then assuming effective cover as 50 mm, the overall depth is equal to 150 mm. Once I get that overall depth, student, then I'll However, the D required is much less than the D provided. Therefore, the section 1 is that the section is under reinforced, and once the section is under reinforced, the steel will govern the design. Means the permissible stresses will reach in the steel first. Therefore, in such a case, this area of the steel is given by MUX is equal to 0.87 FI AST D multiplied by 1 minus FI AST divided by FCK B. B is equal to this 1000 mm. Therefore, now I'll calculate the area of the steel using this formula, and also I'll calculate what is the minimum area of the steel, right? However, now calculating this, now I'm getting the area of the steel which is much less than that of the area of the minimum steel, 0.12 BD, 0.12% of the BD, right? In X direction it has 180, and in Y direction it has say 216, right? Therefore, now that from Flexure point of view it will not govern the design, but this minimum steel point of view it will govern the design, right? Therefore, now I'm assuming that I'm providing the area as 300 mm square and 360 mm square respectively along the both the directions. That what is the spacing of these 8 mm dia required respectively are as 167 and 167 mm square, 167 and 167 mm square. Therefore, provide 8 mm dia rods at a spacing of either 165 mm center to center, 165 mm center to center, right? Once I provide that main steel student, then I need to check for the one-way shear. Therefore, the critical section is at a distance of D for one-way shear. Therefore, at what distance it is there along the width as well as the length directions, I am calculating that B by 2 minus B by 2 minus D, it works out 325, and as well as L by 2 minus D by 2 minus D, it is at a distance of 262. Therefore, the shear force at those sections are respectively P0 BX, P0 LY respectively are 33.37 kilonewton and as well as 53.4 kilonewton respectively along the both the directions. Therefore, the nominal shear stress in both the directions are now given by, say, along one direction, along this X direction is VU by BD, which is 0.2 Newton per mm square. However, the percentage of steel we already provided along X direction as 300 mm square. Therefore, it works out, say, PT as a 0.2. Therefore, from the table 19, if I interpolate for 0.15, tau C is equal to 0.28 for M20 grade concrete, and 0.25, it is tau C is equal to 0.36. Therefore, what is the design shear stress for 0.2? It works out, say, approximately 0.32. Therefore, here tau V is much less than tau C. However, even here the thickness is less than or equal to 150. Even that K multiplied by tau C is also applicable. Even you can multiply with 1.3 multiplied by 0.3, 1.3 multiplied by 0.3. That is also. However, our shear tau V is much less than already this basic value of tau C, that multiplied by 1.3. Therefore, it is okay in single shear. Whereas, let us also check in two-way shear. Therefore, that is how I am calculating the two-way shear at a distance of D by 2 from the face of the column, along the periphery of the column at a distance of D by 2 along the periphery of the column. You are already aware of that. Therefore, now I'll get the shear force. Two-way shear is equal to 142 kilonewton. Therefore, the two-way nominal shear stress is equal to VU divided by the peripheral length along the or the punching area. Punching area is equal to this B plus small d plus D plus small d, right? That is B plus D plus small d plus D, capital D plus small d, right? That is that multiplied by effective depth. Therefore, if I do that, now I'll get the punching shear stress, nominal shear stress as 0.52 Newton per mm square. Whereas, as per this class of IS 456 2000 from page number 58, class 31.6.3.1, page number 58, right? Therefore, I am there in page number 58. Now the code says that that is how it should be checked at a distance of D by 2. Actually, this is applicable for the flat slabs. Even the same is also applicable for the footings also, student. Therefore, now code says that the permissible shear stress should be Ks multiplied by tau C, whereas that Ks is given by this 0.5 plus beta C, where bit, and this value should not be greater than 1. However, beta C is the ratio of the shorter side to the long side of the column or that of the capital, and tau C is the permissible shear stress. For the limit state method, it is 0.25 square root of FCK, and it is equal to 0.16 square root of FCK for working stress method. Therefore, substituting into that, now I'll get this result. Now I'll get this result as say as 0.5 plus beta C multiplied by 0.25 square root of FCK is equal to 1.11, because my beta C is equal to 0.61. Therefore 0.61 plus 0.5 means it is 1.11, but not greater than 1. Therefore, if I restrict it to 1, that multiplied by 0.25 multiplied by square root of 20, it works out 1.11 Newton per mm square. However, you please see that the actual punching shear stress 0.52 is much less than this permissible punching shear stress 1.11 kN per meter square. It is okay. Therefore, it is okay. And also check for the load bearing capacity at the intersection of the column with that of the pedestal, right? Therefore, assuming the bearing bearing stress as per this Codal specification, class 34.4, page number 65. All right, let me go to that page number 65, student. Right? That is page 65, right? Therefore, from this page number 65, I do have shear and bond, right? What the code says is that the transfer of the load at the base of the column, right? The bearing pressure on the loaded area shall not exceed the permissible bearing stress in the direct compression multiplied by a value equal to square root of A1 by A2, but not greater than 2, where A1 is the area actually loaded and having side slope 1 vertical to 2 horizontal, and A2 is the loaded area of the column base. However, now for limit state method, the permissible bearing stress should be taken as 0.45 FCK. Therefore, from this Codal specification, now I'll calculate what is that permissible or allowable bearing stress as 0.45 square root of 0.45 FCK square root of A1 by A2. Then I'll calculate what is that A1. It now works out like this, right? 809250 mm square, and A2 area of this column works out say 86,250 mm square. Therefore, square root of A1 by A2 is almost much more than 2. Therefore, restricting it to 2, that multiplied by 0.45 multiplied by FCK, it works out the permissible bearing stress as 27.57 Newton per mm square. However, what is that actual bearing stress? Where this column is put on that footing or on the pedestal as appropriate, right? Therefore, I do have this result as say a value as say load on the column 140 kilonewton divided by size of the column. Size of this column is equal to 230 by 375. Therefore, the actual bearing stress is 1.62, is much less than that permissible bearing stress of 27.57. I'm assuming that this column is supported on a pedestal, right, of say some 0.6 or 2 feet height, right? Therefore, that 0.6 plus the depth of the footing maybe 0.15. Therefore, just below the ground level, I am reaching at a level of 0.95 or 1 meter from the natural ground level. That is what my assumption, right? Therefore, that is how the design of a footing using manual calculations, right? Once I do that design of a footing using manual calculation, there I have done only just for axial load only, but now I'll use the Excel sheet for doing the calculations for the footing which is actually subjected to a axial load as well as the bending moment about both the direction, right? Mx as well as My. The end columns are subjected to both Mx as well as My. That is the actual scenario. Therefore, now I'll take the help of the Excel sheet, right? Therefore, now there I do have now I'm giving this inputs for this as FCK is equal to 20 and Fi is equal to 500 and clear cover to the steel 50 and permissible bearing capacity of the soil as 200, and whether any increase in stresses is permitted? Yes, as per the code. If at all there are the earthquake and wind loads are there, then it can be increased. But I don't have any earthquake or any other load combination that of the wind. Therefore, now I'll say 1, right? And obviously, then what is that coefficient? If at all it is 500, that coefficient is equal to mu lim is equal to 0.134 FCK VD square. Therefore, I am recalling that. Therefore, is there any increase in SBC? If at all it is a combination of wind and earthquake load, then SBC may be increased. But I don't have any wind or earthquake. Only I have to have gravity loads. Therefore, I am saying no, don't increase. 1 only, right? 1 only. Therefore, now this is the size of the column or pedestal, right? 375 by 230 is the size of the column. Even that of the pedestal also, I'll assume the same. Or even for the pedestal, you can give say 3 inch extra, right? 375 plus 150, 525. Even in other direction, 230 plus 150 or 380 respectively, right? As both the dimensions of the pedestals as appropriate. However, the axial load is equal to 170. Just now we have seen from the manual calculation also, right? And the minimum movement, right? About one direction is equal to from minimum eccentricity 170 multiplied by 0.2. It is equal to 3.4, and also the movement from the other direction is equal to 8.31. Now that is how the actual movements from the STAAD. I'll show the STAAD analysis later, student, right? Let me just conclude this design of this footing from the Excel spreadsheet. Therefore, for this, how much of area required is 0.9 meter square. Therefore, I am proposing L is equal to 1.2 meter and breadth is equal to 1 meter, as you already assumed in the previous assumption. Therefore, there is a 1.2 meter by 0.1 meter. However, my column is of, or that of the, if you are proposing a pedestal, then you give the size of the pedestal, right? Therefore, 0.375 by 0.25. Now I do have this cantilever projection along this 1.2 meter as 0.4125, and the cantilever projection along the width as 0.385. Therefore, now I'll calculate what is the bending moment for this cantilever projection. That is how the variation of the SBC is varying from 86 kN per meter square to 197.4. Now I'll come to that, right? Therefore, that is how the actual SBC is P by A plus mx by zx and my by zy. In the manual calculation, I have not done that. I have just only taken this 141.7 and I have simply proceeded with the design, right? I have not calculated this mx by zx plus my by zy. Therefore, there are the 4 permutation and combination, plus or minus mx by zx plus or minus my by zy. Therefore, accordingly, you will get 4 stresses at the 4 corners of these footings, out of which now I'll take the maximum with plus and minimum with minus, right? And maximum is now working out as 141.7 plus 14.2 plus 41.6 as 197.4. But however, this is just less than the permissible value of 200. Therefore, okay. And this minimum is equal to 86 kilonewton per meter square, but this value should not be negative. If at all negative, then it will lose contact with the soil. Therefore, there is not acceptable by the soil, cannot take any tension, whereas it can take infinite compression also, no problem, right? That is how I am okay in both the checks from maximum bearing stress SBC as well as minimum tension point of view. No tension is occurring. Therefore, the assumed length and breadth of 1.2 by 1 meter is okay. 1 meter is okay. Therefore, once it is okay, then I will calculate the movement along the x direction. Just now we have calculated also 25.19, and the depth required along this direction is equal to 99.16. Therefore, I am assuming already in the manual calculation I assumed effective depth as 150. I am assuming the same. Therefore, then overall depth is equal to 150 plus 50 plus assuming 8 mm dia, 8 by 2 means 204. Overall depth is equal to 204, right? Now I'll calculate what is the area of the steel required. However, the depth required is just 99, but the depth provided is 150. Therefore, the section is unreinforced section. then I'll get what is that mu by bd square. For that, what is that pt by 100, pt by 100, it now works out 0.00276. Therefore now I'll calculate for that what is that area of the steel required, right? For what is that percentage of the steel, is equal to 0.276 from the table of SP 16. Therefore for that I'll calculate what is the area of the steel required. It is approximately 415 mm square, but the minimum steel is equal to 244. Therefore 215 is much greater than 244. Therefore this 415 will govern the design, not that of the 244. Please make a note. Whereas in the manual calculation I have not taken movement, therefore there only the minimum steel was governing the design. Therefore assuming 8 mm dia, I require 121 mm spacing. 121 mm spacing is required. 121 spacing is required. Therefore now we need to provide, let us say 120 I'll provide. Therefore if I provide 120, then the provided is equal to 418, required is equal to 414. Therefore okay. Similarly I'll do along the y direction. The movement along the y direction is equal to 26.33, and the area of the steel required along that y direction is equal to 429 approximately. Therefore 8 mm dia, whereas the minimum steel required is equal to 294, whereas 8 mm dia required is equal to 140. Therefore 140. Even if I provide same 8 mm dia 120, then provided is equal to 502, but which is greater than required is equal to 430 mm square. Therefore it is okay. Once it is okay, let us also check whether this provided depth of overall depth 204 and the provided steel of 8 mm 120 about both the direction, is it okay from one-way shear point of view? Therefore along the x axis, now I'll check for the one-way shear along the long direction or along x axis. Along this x axis, student, therefore their VU, I have calculated VU is equal to 77.7 kilonewton. Therefore nominal shear stress is equal to now 0.518 Newton per mm square, but already percentage of steel is provided. Therefore for that PT 0.279, I'll interpolate using this table. Therefore for 0.15 PT tau C from the table 19, I would have 0.29. For 0.25 tau C 0.36. Therefore 0.2791, what is the permissible shear stress is equal to 0.38. Therefore that 0.38 is interpolated and recall. Therefore that multiplied by 1, I'll not increase the stresses because there are no lateral loads in the form of wind or earthquake. Therefore my permissible value itself is 0.38. However, now immediately I would have a check whether nominal shear stress, yes, 0.51 is much greater than this permissible shear stress. Hence now I would have a warning that revise the design. This is failing in single shear, right? Single shear. Similarly, let us check the two-way shear, right? The critical section is at a distance of d by 2. Therefore now I have calculated what is that shear force from two-way shear point of view. It is 212.61 along this long span direction or x-axis direction, that divided by this shearing area B0 multiplied by D, which is 1810 multiplied by 150. It now works out say 0.78 Newton per mm square. But what is that permissible shear stress is 0.25 square root of FCK multiplied by that K. Just now we have seen, right? KS. Therefore it is 1.118. Even this tau C is greater than this nominal shear stress, punching shear stress of 0.78. Therefore it is okay in two-way shear, but it is not okay in single shear along x-axis direction. Similarly, if I check along the y direction, for single shear, now I have to have the same warning. Nominal shear stress is along y direction of 1 meter 0.4766 Newton per mm square, but the permissible shear stress is only 0.38. 0.386 is much less than 0.47. Therefore now revise the design, whereas it is okay in two-way shear. Now we can see that nominal shear stress in two-way shear is 0.81, whereas the permissible value is equal to 1.18. Therefore it is okay, safe in two-way shear. Therefore water that we have designed just for axial load of 140 is not okay. If at all I am adding the bending moment about x as well as y direction, therefore I need to refine this design. Therefore now I'll increase the effective depth. There is no other option but to increase the effective depth is the first option, or increase the steel, the second option. Increase the depth or increase the steel. Therefore please see that right, the depth is okay from flexure point of view, but the depth is not okay from single shear criteria, single shear criteria. Therefore now I'm increasing the depth from single shear criteria. Let us say the overall depth is equal to 250 or say 254 I'll provide, so that my effective depth is equal to 200 mm. Therefore in which case if I do that, now what I'm getting here is the spacing of the rods will change 165. Let us say I'll provide 165 now. Okay, right, I can provide. Therefore I require 304. I am providing the same 304.4. It is okay. About small span direction, even along the large span direction, I require 8 mm dia at 164 point odd, but I am providing 165. Therefore required is also the provided. Therefore okay. Hence along the short span direction, previously what I have checked using 8 mm 120 dia with a thickness of 200, that was failing. But now I increase the depth from effective depth of 150 to an effective depth of 200, but I have decreased the steel. But now also it is not okay along the short span direction. Now you can see that yes, revise the design, because still tau v 0.31 is much greater than that of the permissible shear stress. Therefore there is no other option but to proceed with I already increase the depth. Now what I'll do is I'll increase the steel. Therefore let us say 8 mm dia 150 I'll try to do, right. Therefore 150 along x direction as well as along the y direction 150. Is it okay? No, it is not acceptable. 0.31 is much greater than 0.3. Therefore then if that is the case, now what I'll do is I'll say 125 and 125 respectively, right. 125 125. Yes, is it okay? Yes. Now the code is saying that along the x direction, long span direction, the actual nominal shear stress 0.31 is much less than the permissible shear stress of 0.32. It is safe in one-way shear along the long span direction. Previously it was failing along long span direction, right. It is also okay in two-way shear. Now you can see it is safe in two-way shear along the long span direction, as well as it is okay in the single shear along the short span direction, y direction, and also it is okay in two-way shear along the long span direction. Therefore this is my final dimensions, right. Therefore provide 1.2 meter by 1 meter of depth 0.254 254 mm overall depth with a steel of 8 mm dia 125 mm about both the directions. That is how the design of the footing subjected to biaxial bending, student. However, I have not calculated using manual calculation. I have not calculated for biaxial bending, right. Therefore I have now calculated for biaxial bending, right. Once we see this, now let us move to the top, the STAAD analysis and designs, what the STAAD is saying, right. Now let me enter into this STAAD, right. This is how that my 3D model of this beam and column frame. I do have 1 2 3 4, right, 4 columns, right, whose dimensions now we'll see, right, are 230 mm width by 375. Even the width of this beams is 230 by 575, and the width of this beam is equal to 230 by and depth is equal to 425. Whereas this central beams, right, B8 B9, right, these are the B8 B9, these are B7 B10, these are B1 B2 B3 and B4 B5 B6, right. That is how the beams what we already manually designed, right. Whereas this width is equal to 230 divided by this depth is equal to 525. Both this longitudinal 3 beams as well as these 2 beams are of 525 depth, right. Once we see this, now let me go to the top the page setup student. Now I'll define that this is the job information. I'm giving this, I'm saying ground floor RCC building for the structural engineering client, and designed by which engineer, and checked by which engineer on which date. I'll give. Then I'll move to the top, the next page, geometry, right? I'm defining all these nodes, right? Node number 1, 2, 3, 4, 5, 6, so on and so forth, right? The node number 1 is at 0, 0, 0, and node number 2 is at a distance of, right, the distance of 4.915 and 0, 0, 0, right, 0, 0, and node number 3 is at a distance of 9.83, and node number 4 is at a distance of 14.745. Now I'll move the vertical direction. In the vertical direction, by I'll go to the node 5. Node 5 means I'm moving in the vertical direction by 3.2 meter, right? Same, right? Like that, I do have the node 5, 6, 7, 8, right? Then I'll come in the z direction by a distance of say 3.77 meter, 3.77 meter. Therefore, once I come by a distance of 3.77 meter, student, then I'm having this as say an off, right? This 13th, sorry, this ninth node is at sorry, right? I do have all these nodes. Then I'll go to the top, the element connectivity table, right? This first beam is connected between let me just initiate the names of the number of the beams, right? That is just initiated, right? Then I'll give the node 9 is at a distance of 0, 0, 0, 3.77, right? Like that, I'll assign the other nodes up to the 16th node, right? Once I assign these nodes, then I'll go to the top, the element connectivity table, right? This first column is connected between the node 1 and the node 5, right? Like that, you see the second and third, right? Third, fourth, and so on and forth, right? That of the 11th column, right? 11th column, the element connectivity table is established, right? Once I conclude this geometry page, student, I don't require any other information. Then I'll quickly move to the top, the property page. In general page, I am there in the property menu, right? A toolbar. Now I am defining these columns are of 230 by 375. These are the 4 columns, and their orientations also you please see like this, right? Their orientations, right? 4 columns, right? And similarly, I'll define the top, the beams, 2 end beams of 230 by 425 already defined, right? And these 3 span continuous as well as these single span intermediate beams B8 and B9 are of 230 by 525. Once I define these, I don't require any beta angle. Therefore, even I don't have any specification. In today's class, I'll not go into the specification, student, right? Then I'll define the supports. All these 1, 2, 3, 4 and this 9, 10, 11, 12 are presumed to be fixed because they are embedded into the footing or the top of the pedestal, which is presumed to be fixed, right? And the footing or pedestal is not sinking, therefore it is presumed to be rigid, therefore rigid support, right? Then once I do the support definition, student, I'll move to the definitions. I don't require any earthquake or other definitions. Directly I'll go to the self-weight dead load is now defined. Then the second one is that of the floor loads, right? Floor loads. Now let me see the floor load definition, student. Now I'll initiate, I want to see the loads also, therefore I've initiated the loads, right? Therefore now you can see, right, I'm having the live load of a floor load of total floor load, or we have calculated manually as 8 kilonewton per meter square. I have calculated manually, right? Actually it's not live load, student, right? Actually this itself is the loads from the thickness of the slab and the floor finishes, the plaster, the ceiling to the plaster, etc. Actually it is not purely live load, student, please excuse me, right? Therefore this is 8 already shown, right? 8 kilonewton per meter square. Therefore if I take that, now you can see that on this end beam number 15 triangular load is varying from 0 to 15.008, whereas on this beam 8, you can see on this beam 15 it is varying from 0 to 15.088 kilonewton, right? Whereas on this beam 5 it is varying from 0 to 15.08, and it is then it is constant, right? Later onward from 15.08 to 0, right? That is varying in a trapezoidal fashion on these beams 5, 6, 7 are on 12, 13 and 14, 12, 13, 14, right? There is also variation of the loads, right? Once I do this definition, student, then I'll go with that of the load combinations, 1 multiplied by dead load and 1 multiplied by the live loads, right? Therefore, once I do that, now I'll define the analysis also, right? Analysis, perform analysis. Then I'll go to the design page. Now I'll go to the design page, wherein I'm there in concrete page. I'm defining this IS 456, right? I'm there in this, right? Code Indian. Clear cover to these beams 25 mm and clear cover to the columns is equal to 40 mm, and all members are M20 grade concrete, and main steel Fe 415 grade, Fe 500 grade steel, 500 Newton per mm square, and that of the secondary steel is 415 Newton per mm square. Just now I already explained that the column is having the effective length factor about Y as well as Z as 0.65, and the maximum main steel is 20 for all these beams, and maximum secondary reinforcement is equal to 10. Now I start bar combinations with MD. The minimum steel combination steel is 12, and maximum diameter of the combination steel is 20. Then end bar definition, and minimum main steel as per the IS 456 are SP 16 and SP 34, right? And 12 mm dia, and minimum secondary steel 8 mm dia, right? And I'm saying the maximum percentage of steel is equal to 4, and reinforcement 0. Reinforcement 0 means the ties, not that of the spiral stirrups, right? R phase 4 means reinforcement provided equally on four sides, right? Therefore, using that, now I'm saying that design these beams and design these columns and concrete take. Therefore, once I click analyze, now you can see that just in one moment I got the analysis, student. Once I get in 1 second only I got, let me just close and quickly do the analysis, student, right? Analysis. Once I do that, I am getting the output at within just 1 second I am getting that, student, right? Therefore, there is advantage. There is advantage of running these using the softwares, either STAAD or that of the e-tabs, right? That is how I'm just clicking. I'm afresh. I'm just clicking for your convenience, and I'm analyzing. In just, you can see in one click moves, just within you see the runtime is only just 2 seconds, student. 2 seconds, right? Just within 2 seconds I got the output. And now I'll check whether any failed members are there. No, right? Even whether any adequacy check is required. Yes, no, they are not failing. Therefore, once these are through and through, then I'll move with that of the check for the beams as per IS 456, that of the beam number 5. What is that beam number 5? Let us check, right? Let me just re-give that of the node numbers and beam numbers, right? This is my beam number 5, student. This is the beam number 5 where I am getting the steel, the steel as negative steel as a 254 mm square and positive steel as 193, and the stirrups as 8 mm dia, 165 mm stirrups, whereas we have designed the sixth beam, right? There also the negative steel is 231 and positive steel as 193, and stirrups 2 mm dia as 2 mm dia, 2-legged 8 mm dia, 300 mm center to center. Let us compare this with that of the manual calculation, students, right? What I got there for the design of these main beams, right? Main beams, right? Just a moment, student, right? What I got there for the design of these main beams as manually is this result, right? This result, right? That already done the design, right? Like this, right? Therefore, there is the design for the main beam, student. That is how manually calculated. There I got manually the movement 40 kilonewton meter. But let me check from the STAAD. I'm getting a result of 47.1 kilonewton meter, right? Let me go back to that STAAD and check first of all what is that. I'll go to the post processing, student, right? I'll do that post processing, right? Post processing for this load combination of 1.5 multiplied by dead load and 1.5 multiplied by live load, right? Therefore, I'm there in that. Therefore, for this now I'll see the graph, right? Therefore, for this I do have the bending moment varying at the left end 17.4 kilonewton meter to 50.8 kilonewton meter, whereas the positive bending moment at the midspan is 35. Whereas I have analyzed this second beam manually. However, using STAAD I am getting 47.1 to 47.1, and at the midspan I am getting 21.4, whereas the shear force I am getting 45.4 to 45.4. This is the mirror image, right? However, how much I got from manual calculation, right? From manual calculation I got 40 kilonewton like this, right? Just a moment, student, right? 40 kilonewton, right? This is how manually I got 40 kilonewton, right? Whereas from STAAD, right? This 40, right? Just a moment, right? This, right? This is how 39.48, assuming the intermediate beam which is fixed at both the ends. But from STAAD I am getting that result as 47.1. Therefore, my STAAD is exact, because after all that 3-span continuous beam is assumed as just a fixed beam. Therefore, there is a lot of change in assumption. Actually, there is a continuous beam, right? Actually, even this 3-span continuous beam is not analyzed as a 3-span continuous beam, right? Just taken as 1-span beam only for manual calculation as that too fixed. Therefore, there's a lot of change in assumption. Therefore, my STAAD result is correct, which is 47.1 kilonewton meter. However, if I take that STAAD 47.1 as my correct result, therefore this 39.48 is almost 16% error. Manual calculation is 16% error, right? 16% error, right? Likewise, this positive bending moment 19.79 from manual calculation, but from STAAD I am getting 21.4. Therefore, my 21.4 from STAAD is exact. Almost here and there it is exact, right? Compared to that of this 19.7. Therefore, this 19.7 is approximately 7.8% error. Now you may wonder why we are having almost, right? Why we are having 16.2 and say 16 and 8% error, right? Because I have considered only one span continuous, right? Even that here the STAAD what I have done is a 3D analysis, right? Totally it is a 3D analysis, right? Whereas in the manual calculation just I have taken this beam only, right? Assuming both ends to be fixed. Therefore, there's a lot of change in assumptions from that of the analysis, that of the 3D analysis of that of the STAAD to that of the manual analysis, assuming only one beam which is fixed at both ends. Obviously that much of error will obviously come, right? That is how the change in assumptions from manual calculations to that of the 3D. Therefore, I can say that the actual RCC frames are that of the actual structures should be done using 3D analysis only. Manual calculations will never match with that of the STAAD 3D analysis, which are almost more exact results. Even in the previous videos we have seen that STAAD will give exact result with that of the manual calculation if it is modeled perfectly, but I have modeled perfectly, but manual calculation I have not modeled perfectly. I have so many assumptions. With that assumption only I got the manual output. Therefore my manual calculations are wrong, therefore my STAAD outputs are correct, right? Like that. Now let me check what is that movement in this beam. It is varying from 7.7 to 25.6, but what I got there from manually I got, right, this result, right, varying from, right, instead of 7.7 I got 22.19 from manually, almost 188% error student. Why? Because I do have a 3D analysis, whereas at the midspan I got 11.09. From STAAD I got 25.6. just see this, right, 25.6. that much of error is there, right? Therefore even in the midspan I do have a movement varying from 9.68 to the other end 9.68. the positive bending moment is 51.9, but in the manual calculation what we got, right, is this one, right? You see, right, 41.07 instead of this 9.68, almost 324% error student. Not acceptable, right? Therefore my manual calculations are almost not acceptable, because I have not done a refined 3D manual analysis. I cannot do 3D manual analysis, student, right? Therefore not acceptable, right? Similarly, the positive bending moment using this manual calculation I got 20.53, but actual bending moment at the midspan from the STAAD is 51.9. almost compared to that, almost I do have roughly 61% error. Therefore my manual calculations are of no use for the beams. Even let us see what is that output for this three span continuous. There I do have all these, right, compared to the top this STAAD, right? I am saying that for the first beam I am getting negative steel required is equal to 254, positive steel required is equal to 193, right? 254 193, whereas 231 193. Therefore 231 divided by even 12 mm dia if I provide I require 2 point odd value, or say 231 divided by 113. I require 2.04. Therefore I told you provide 312 mm dia, 312 mm dias, top steel and bottom steel 193 is required here, whereas here in the previous case it required 193. Therefore either 193 divided by 113, 1 point odd value, or say 212 mm, or even you can provide 312 mm dia as the bottom steel, both. Now I'll prefer that to provide 312 mm as a top steel as well as the bottom steel. However, manually also I got the same result, right? Even you can see the stirrups I got manually also 2 mm dia, 8 mm dia stirrups at a spacing of 300 mm. Let us check that, right? 300 mm spacing, right? 300 mm spacing, right? 394, but later onward it was restricted to 300 mm. But now STAAD is giving say 295. Therefore it is in line with that of the manual calculation, because the minimum shear reinforcement is governing the design. Here it is matching because it is governed by the minimum shear reinforcement. Therefore all these manual calculations are okay with that assumption only, but they are not refined calculations. Now let us see even that of the designs of the columns also, student, right? Whereas this end column is subjected to a bending moment at the bottom 8.31 kilonewton meter to that of the at the other end, right? At the other end 17.4, right? At the top 17.4, right? And it is subjected to an axial load of 77.2 at the bottom, whereas manually I calculated 140. There is a lot of difference, right? Almost right, my 77.2 is exact, but manually I got almost double that value, 140. Not acceptable by the code, right? That is not acceptable, right? Even now let us check for that of that this intermediate column, the movement is varying from 1.82 to 3.67, but here you see the axial load at the bottom is 159, whereas manually I got 140, almost okay. 140 is in line with 159, but movements, you see there the movements were almost were assumed 0, because here from both 0, but from this direction it was assumed as 40. Therefore this column was presumed, it was designed manually to subjected to a axial load of 140 kilonewton and no movement, mx is equal to 0 and my is equal to 40 from manual calculation, whereas this column was designed for manually subjected to a manual axial load of 140 kilonewton and some 23 kilonewton from this and 40 kilonewton from this beam, whereas this column is not subjected to that much of bending moment. Student, please see from STAAD I do have just 77 kilonewton axial load subjected to a bending moment of just 8.3 kilonewton only, right? From one direction, even from other direction also the same bending moment may be assumed, right? 8.31, right? Like that, this column is subjected to an axial load of you see 159 kilonewton subjected to a bending moment from one direction as 1.8. However, whether is it acceptable by the code, right? 159 multiplied by 0.02, no, that is not acceptable. Even that 1.82 is not acceptable, because that 159 multiplied by minimum eccentricity 20 mm is 3.18. Therefore 3.18 will govern the design about the both the directions, right? That is how the designs of the columns are also done. Right? Like this, right? Just if I click the design of the column, student, now what this is saying that it is designing for that actual load and actual movement, right? It is saying that 340 mm square is required, or AS percentage of steel required is 0.52, but that is not acceptable. 0.8 percentage is minimum dimension. Therefore 230 multiplied by 375 multiplied by 0.8. Therefore minimum I require 690 mm square is required. But even let us see what is that in the central column. Yes, there also it is saying that no, I did just require 143 mm square, not acceptable, not less than 690. Like that, if I click the other columns, there also I am getting same 143, right? 340, right? 340 and 143 same do. Therefore that is not acceptable. Therefore at least you provide 690. However 690 0.8 percentage, right? However, you provide already in the manual calculation I have provided 1.5 percentage, student. 1.5 percentage. There I got almost, right, some 1268 mm square, but I have provided 816 mm dia bars, 816 mm dia bars, like this, right? 816 mm dia bars, right? Therefore that will govern the design. Let me just show that design of the column manually, right? That is how provided. I have just initiated the column, the interior columns, right? Manual design, but that manual design is not applicable now, right? Even I have designed which are subject those end columns, right? Those end columns subjected to the biaxial bending, right? They were subjected to this much of load, 140, 40, 23, but that is not that. As per the STAAD, now I have just only some 53 and some 3 point minimum eccentricity, right? Some 3.4 kilonewton meter only. Therefore for that, what is that? STAAD is saying that only 142 and 342 mm square, but that is not acceptable. You restrict to say 0.8, 690. It is left to you, student, right? Either you provide, right, that divided by 113, right? You require 6.1 number of 12 mm dia bars. Therefore either you say, if you want to provide 1 2 3 4 8 number of, right, 1 2 3 4 5 6 7 8 number of 12 mm dia, if you provide Therefore 8 multiplied by 113. Therefore provided is equal to 904. Required is equal to that 690. Therefore okay, right? And also you provide the stirrups. Just now we have seen how the stirrups must be provided, right? That is how we have said that provide 8 mm ties at a rate of 200 mm center to center, right? That is how the design of the column, also from the STAAD when compared to that of the design of the column from that of the manual calculation, student, right? That is how the variations of the bending moments also, right? That is how the, or even that of the forces you can see, right? That is how we can see that negative bending moment at the continuous support, right? Positive bending moment, right? Negative bending moment, right? Positive bending moment, right? That is how the variation of the bending moment along the three-span continuous beam, whereas then bending moment variation for the exterior beams as well as the interior beam. Now even you can see the variation of these. Let me show the numeric values also. Just a moment, student, right? Just bear for a moment, right? That is how the numeric values also, right? I have to have all these values, right? It is varying. The negative bending moment is varying from this 17 to 34 positive to the top this, right? To the top 50 to 21 to some 50, 34 to 37, like that, right? Whereas for the exterior beams, it is 0 almost, right? Varying from a small value of some 7 to central moment 25 to that of say 17 kilonewton at the end, right? Like that. Even for the mid-span beam, central beam is varying from approximately some 9.6 kilonewton to central positive bending moment of 51, that will govern the design, to that of a small moment of 9.6 kilonewton, right? Even you can see the variation of the bending moment in the columns, right? It is varying from the bottom 8.3 to at the top 17, right? Same 8.3, whereas the intermediate columns, it is varying from just minus 3.6 to 2.8 only, right? That is how the variations of the shear forces and variations of the bending moments, student, right? Variations of the bending moments, right? I hope you understood the discussions what we had in today's class, student, right? In today's class we discussed the analysis and design of that of a ground floor single story RCC building done by manual calculation, right? There we have seen the slab, beam, column, footing manual designs. Even I have done the designs using Excel sheets. Later on I have compared that with that of the STAADPro. Therefore I have concluded that STAAD is giving exact results compared to that of the manual calculations, right? Therefore that STAAD result can only be accepted compared to that of the manual results. Therefore, because the manual designs are done assuming only one beam continuous only, one beam, right? There is an error in assumption of the manual calculation. Therefore they were not governing the design, right? Therefore here the analysis that of the STAAD is done, that of the 3D frame subjected to exact loads what you have considered in manual calculation. Therefore my STAAD results are exact. Hence my STAAD results are the exact results compared to the top this one manual calculations. I think now we'll try to conclude the discussion, student, right? If you like the discussions what we had in today's class, right, don't forget to click like, share, subscribe, comment and turn on notification to our YouTube. We'll meet with another discussion. The discussion is on ground plus one story RCC building design by STAADPro, right? In the next class. Till then, bye bye, students.